Hello everyone. So today Selman is going to tell us about delegating private quantum computations. I guess this is the third part of the MBQC sequence. So Salman, please take it away.
Thank you. So I must say that MBQC will be noticeably absent from this. We'll make the connection to the previous protocol for a universal blind connection shortly, but this is actually a fundamentally sort of different task, cryptographic task, as well as a using not MBQC as the model, but just sort of it uses a little bit of teleportation, so in that sense, it's related, but it's sort of more couched in the circuit sort of point of view. So we're going to talk today about delegating private quantum computations. So what does that entail? So the goal here is that you have a client which is to delegate to a server a quantum computation. Uh, so these are the two main parties, the client and the server. Delegate to a server a quantum computation without the input or output being known. To the server, of course. So much like blind quantum computation, the idea is that sort of with quantum computation, you envision a sort of a state of affairs where quantum computers are relatively expensive or they're not like sort of local to you. And so you want to, as a client, you want to delegate this computation you want to do to a quantum resource, to a quantum computer, but you don't necessarily want the server to know what exactly it is that you're doing. Different from the blind quantum computing protocol is that the computation itself, that is the string of circuit elements that you will perform, they will be public actually. So maybe something to say here, the computation so for example, the gate set, gates performed, are entirely public. So the server knows them. So, you know, if you're doing something like, um, you know, if it requires phase, Hadamard, you know, so on and so forth, these are going to be known. These are in the public domain. So the task is a little bit different. What you really want to do is hide the initial quantum state that you're feeding into the computation, and also the actual outputs that you will use should also be hidden. So just to compare with blind quantum computation, there's some differences. One is that because, well, with blind quantum computation, maybe I should recall 1, 2, 6, 7, 8. You had these arrays, these brickwork arrays. Oh, why is this not copy? You had these brickwork arrays, and the reason for introducing these was that you wanted a universal sort of substrate, a universal resource with which you could implement any gate that you wanted. But it was quite redundant because what ends up happening is in order to do just basically you have these 8-layer blocks like these, and these could be used to actually perform any gate that you want. So how did that work? So it worked like you had these angles, delta xy, where xy labels the qubits in this node. By the way, the lines represent entanglement. So you had this delta xy, which was chosen from a set of 8 possible angles, k pi over 4, k in z mod 8. So how did it work? So you had to send an angle from the client to the server for every one of these. Well, I guess this is not 8. Sorry. 1, 2, 3, 4, 5. 1, 2, 3, 4. Maybe I listed too many here, but the idea is that for any particular gate that you wanted to perform, I think you need just a subset of these, perhaps like, I think it was just these perhaps. And you could perform any gate that you wanted using just these. And so Alice or the client had to send to Bob log base 2 of 8. Because these angles, there's 8 of them, right? So for every single site, you had to send 3 bits. And then you also needed to, let's see. So you have 3 bits, and then you have 8 sites for each gate that you want to do. So you have to actually have 3 times 8 equals 24 bits of client to server. And then also when the server is sending you your outcomes back, you also have these outcomes S, X, Y in Z2. And so you have, and so then you also have 8 bits for each gate that go. In addition to this, the client needs to be able to prepare 8 possible input qubits. And these input qubits can have weird rotations like pi over 4. So this is actually quite a bit of backward and forward communication between client and server, and also requires some more computational resource on the client part. So we will look at delegated quantum computing. We're not trying to hide the computation itself. So what does the client have available? So maybe so in this picture, the client is able to do what? Pauli X and Z, I guess you could call them rotations or unitaries. That is, you're applying Pauli X or Z on a particular qubit. This is for the encryption. Basically, for those familiar with like super dense coding or teleportation, those are kind of related protocols. You have these 2 bits that you use. The idea is that you use a quantum one-time pad, which is going to be like doing teleportation, quantum teleportation, but not sending the bits to Bob, essentially. That's kind of what you want to be able to do. And what else is the client able to do? They're also able to prepare states from the following set. So they can randomly choose these states. There's a more compact way to write these. Plus 1. So this is plus or minus. This is the plus or minus state. And these are the plus or minus I1. These are the plus or minus 1 eigenstates of the Y, Pauli Y operator. So as opposed to being able to prepare one of 8 states, now you only just need to be able to prepare one of 4. Server, and so the server has a universal gate set. And that's going to be somewhat not a minimal set, but X, Z, H, P, controlled not, and the T gate. I use the notation somewhat different from the paper, which calls the T gate, the R gate, but we often use T for this, so which is a pi/4 rotation around the z-axis. And so the idea is going to be as follows. The client is going to encrypt using basically applying random polys to each of the qubits that they send to the server. And the idea is going to be for every gate that the server performs, the client is going to know which gate is being performed, and they're going to try to update the keys, the encryption keys, and then decrypt when they get back the actual qubits. So maybe I just say this in passing, and we will see it eventually. Each gate can be performed using a gadget. And then client updates the encryption key. Okay. And so I will say what the gadgets are a little bit later. So if you're saying, well, I don't know what those are yet, we'll get to it in a second. So maybe any questions so far? Okay, so I think I might have talked about this last time, but I can't actually remember. What is this one-time pad? So classically, what the one-time pad is actually just if I have some bit J, that's the actual bit that I would like, that maybe contains some sort of key. What I do is I modify this bit by R, where R is a randomly chosen bit. So if you do this, in this case, the client would know what J is and also know what R is. And then the server maybe performs some computations on J, but ultimately the client knows to undo J, or sorry, the additional bit R, and they know exactly what it is. So in the quantum case, I can't recall. I think it was in my notes, but I didn't recall if we actually went over it. The idea is this related to teleportation. You have two random bits, A and B, and you randomly apply XA or ZB, depending on this. And the idea is that essentially you have what does the server see in this case? You have basically some quantum channel, which means you have a probabilistic mixture of unitaries depending on these two bits. So from linear operators on C2 to linear operators on C2. I didn't introduce this notation, but the idea is that you've sort of implemented a quantum channel wherein for some linear operator A, you're doing this thing. 1/4 is for the probability of each possible pair of bits. You sum over those bits, and you do XA, ZB. Sorry, should be A. ZB, XA. Unassigned piece of homework, show that this will yield the totally mixed state when you're dealing with a single qubit. So I don't think it should be hard to show. In principle, you just need to show that this acting on the identity is equal to the identity, so it's unidal, and then acting on any of the Pauli matrices X, Y, or Z is equal to 0. And then you can expand A in this Pauli basis, and that basically gives the result. So you have that for any quantum state, the effect of this thing is going to be the totally mixed state for a single qubit. So Bob gets absolutely no information from manipulating this thing precisely because he doesn't know these bits A and B. Okay, so let's see the first protocol now that we sort of know what the one-time pad is. It will go as follows. Let's see. No questions. Okay. So it kind of goes like this. So client encrypts each qubit with the quantum one-time pad. So you just have for each qubit that's in the circuit, the client applies this random unitary like this, and then sends it to Bob. So I'll say A to say that this is in the possession of Alice at first, and then this is sent through some communication channel to Bob. Just to make explicit that now Bob has access to the qubit. Now, in the second step, so server performs circuit gadgets. I guess I should say in G, and client updates the key, the encryption key. So maybe it will help to just give a little bit of the punchline away. These encryption, so these gates, a lot of them are Clifford gates. So what's going to end up happening is that you're essentially using conjugations through these polys, and you're going to pick up additional sort of corrections. So as you apply Hadamard phase and some of these other things, you'll pick up, you'll modify these A's and B's, and you'll be able to sort of track what this encryption key is efficiently. The only one to sort of worry about is this non-Clifford gate. But then there's a sort of nice way for dealing with that one as well. And let's see if we can't just this. And the third one is that the server returns the output register to the client. Register to client, and client decodes or decrypts. Okay, so what are these gadgets? So let's go ahead and discuss how this works. Any questions so far? It's more or less straightforward to follow, or?
I have one. Yeah. So, I mean, I guess since I'm not very familiar with the general scheme, so I just want to make sure. So the psi in the first part, so this is a single qubit state, right?
Yeah,
Uh,
but you say that I have an n qubit circuit, right? And then I will perform these locally on each, I will perform these local poly rotations according to A and B for each qubit.
oh, okay. So it can be any qubit number.
Yeah.
Then, okay, we can track these ABs because what do you mean by the circuit gadgets here? Do you mean the unitaries in
So I will introduce them, just that's the very next thing. But the idea is going to be, I think, straightforward to understand is that you're going to have these gates, which could be Hadamard phase. They could be poly X or Z as well, CNA, and also the T gate. And essentially, the gadget is just going to be rewrite rules that tell you how to modify A and B in a certain way so that you can undo the poly corrections after each gate. So you'll see the example, but basically you want to just track these A and Bs. They'll change. For example, if you apply a Hadamard, the A will flip to B, the B will flip to A, but you should know that so that at the end of the circuit, you can undo this.
Okay, so the scheme is this psi. I think it's at first in Alice's location, and then she just applies these channels or use unitaries
Yeah,
on
unitaries.
randomly, right? So you can just choose them randomly,
Yeah, she chooses A and B randomly. That's exactly right.
and then sends the state over to Bob, and Bob applies these gadgets, which I assume some sort of unitaries.
Yeah.
And then, at the end of the circuit, the measurements are performed by Bob, and then he sends over the outputs back to
So I actually I think maybe I didn't say this. The client also can perform the measurements. So what Bob does is actually to return the quantum state back to the client.
Okay. Okay. And then Alice performs the measurements. And then what do you mean by
So what Alice does first is suppose just I will give something psi and then this is Alice's, and then she applies XZB. And we don't actually care who's performing it. So now what's going to happen is, say this is going to be a Hadamard applied on this. It's just HXAZB psi, something like this. Say this was just the circuit that we're running. What we actually want to do is conjugate this through. So it will be ZA XB H psi, right? And maybe it was better to say this. Now this is in Bob, Bob, Bob. And now you send this precise state back to Alice. Nothing changed. I'm just saying that now Alice is in possession of it. And now what Alice wants to do is, because maybe she wants to measure this state or do something else with it, now she needs to decrypt this by applying, now she will apply XBZA to undo this.
she has the list of unitaries, I guess, does she?
Yeah, this is public. She knows exactly what unitaries are being performed.
Okay.
So she knows exactly, okay, now I need to apply XB and then ZA, and she knows how to track these polys. And she will perform this, and then now when she applies that gate there, you're just left with H psi, and she can measure it or do whatever.
Okay. Okay.
Okay, so there's a couple of things. Let's see. Honestly, these are more like identities than gadgets. I will sometimes use the following notation just to make my life easier. Psi AB XA ZB psi. So if I measure in the computational basis, and I will use dotted lines for classical outputs. Then if the outcome, so the outcome of this thing will be the outcome of the actual measurement M plus A, where A is the bit associated here with X. So Z is not doing anything. when I do a computational basis measurement, but XA is just flipping the outcome. So, I mean, should the client tell the server to measure something, she knows how to actually undo the measurement outcome. So this is like the classical one-time pad. So you can also do, I will maybe treat these together because they're both very simple. You have, if I want to do an X unitary, what this actually does is it applies an X to XA ZB psi, which up to overall sign -1 to the B, yes, XA ZB X psi, and a similar sort of relation holds for Z. So this is up to overall sign, which we don't necessarily care about. You've implemented the X gate, and you just have, and the client doesn't have to do anything to modify the input bits. They know exactly how to apply these. It just stays the same. So you could say the keeping track of the keys is the trivial operation. A goes to A, B goes to B, and the decryption unitary is going to be ZBXA, which the client applies when they receive the qubits again. Okay, so what about like Hadamard? We already kind of did this. So the idea is that you apply Hadamard to XA ZB psi. We use one of the defining properties of Hadamard, that HXH equals Z. So this one is going to be equal to ZA XB at H, sorry, there should be an overall sign. A plus B, H psi, which is overall equal to XB ZA H psi. And so here we have the map. We keep track of, sorry, just the opposite. A goes to B, B goes to A, and the decoder, or this decryption unitary, is going to be precisely ZAXB. So more or less, this is the sort of pattern. I will maybe, for a couple of these, maybe not be so precise. So for the phase gate, we have that P is applied to XA ZB acting on psi. So we want to sort of conjugate these through. There's this part, yeah, PX P dagger equals Y, whereas PY P dagger equals minus X. So if you want to conjugate this through, and also that P, the phase gate, is diagonal, so PZ P dagger is equal to Z. So after you sort of use these identities, what you get is precisely something that looks like yeah, so there's going to be a slight trick when I see a Y here. Maybe I just do this one to give the flavor of it as well. So PXA is going to be the same as px is equal to minus I zx. Sorry, I think this is just I. This is yp, which is equal to I zx, or maybe easier, minus I x z p. So I will use these, and I'm going to end up, after flipping everything through, x a z a plus b, phase acting on psi. So I again have another easy rule. A goes to A, B. You have that this thing is Z plus
I
B.
I have a question here. Let's
Yep.
sorry, X went to okay. No worries. Yeah.
Yeah, I mean, I could be have messed up a sign somewhere, but I think,
Yeah, it's not important, right? We don't care about the signs, I guess.
yeah, I think maybe I'll just, to be safe, it's something like this.
Because the X will go to Y and Z will stay. So you're combining that, but maybe there will be some phase. Anyways, okay, yeah.
Yeah, there will be some eyes floating around, but like you said, we don't care. But essentially, the idea is that you pick up an extra Z from this conjugation on X, and that's where this is coming from. Okay, so C naught. Um, so this one is basically, I will try to not do this in so much detail. The idea is now I will have maybe this is a bipartite, a 2-qubit thing. So I have 2 quantum lines, and I'm applying this. Maybe no need to draw the circuit, actually. I'll just apply it directly. So XA, ZB, tensor, XC, ZD, acting all on a 2-qubit state psi. And then we will apply controlled knot from 1 CX 1 2. Maybe this can be 1 2 like this. Yeah, so how do we update this one? This one will end up being equal to what you really need to know is that CXIJ acting on X on the control qubit has this equal to Xi tensor Xj. Whereas if I apply the controlled knot on the target, if X is acting on a target, leaves it unchanged. Similarly, Xij, Zi, Cxij. This one leaves this one unchanged because the control is depending on Z. So this is just Zi, and then Cxij, Zj, Xij equals Zi, Zj. So basically, once you have this thing, and so I will not derive the exact form, but you can see that you pick up some additional factors of X if you're applying it on the first, if you're applying C naught on the first X. And then the same thing for Z on the second qubit. So you get something that looks like XA Z B plus D tensor. Okay, yeah. Tensor X A plus C Z D Cx psi. So again, this is coming because when I apply Cx on the first qubit, I am going to, hold on, all of a sudden. Sorry, let me check something very quick. Okay, this is the right form. Okay, I'll have to go and check this. But the right-hand side is correct. So the way that the client updates the keys is A goes to A, B goes to B plus D, C goes to A plus C, and D goes to D. Okay, so now we should go to one of the main sort of innovations of the paper is how to perform this non-Clifford gadget. So the other ones can be performed non-interactively. So what that means is so it just means that the client encrypts the qubits and then the server performs the gate, and the gate is performed and the client knows exactly how to update the encryption key. Non-Clifford gates are going to be somewhat different. So what's the picture look like here? So first, let's look at a naive attempt at this. So the naive attempt is to do the following. You apply the T gate directly to XA ZB acting on psi. So some people might notice that what's going to end up happening here is that you pick up, because there's this identity Tx is equal to X, Z, P, T. So you can sort of show this identity. What you get is that you have XA, Z, A plus B, P, A, T, psi. So this doesn't work because the client doesn't have access to the phase gate. So so you have to do something else. I mean, I guess you could pump up the power of the client and maybe that fixes this problem, but it seems that there's another solution possible that doesn't require you to do this. So how does that one work? You have that the client has encrypted one of the qubits that we want to apply the T gate to. And then there's, it's a little bit of a complicated circuit. So you also have another. Okay, this is going to seem a little bit confusing, but bear with me for a moment. These gates here, I know I just said that the client doesn't have a phase gate, but they do have the ability to randomly prepare these states, which I mentioned much earlier, the plus or minus or the plus or minus, let's see, here. I did say that the client has the ability to prepare these. So that's essentially what you're doing when you write down this, this form right here. This either flips it or it rotates it. So the Z will flip this to plus to minus, minus to plus, and then the PY will move it from a X eigenstate to a Y eigenstate. So this is also allowed for us. So this stuff is happening on the server side. This stuff is happening on the client side, I guess. Okay. This gets measured. And then this is the output that we want, which I will call phi. And then we also have a random bit x. X is equal to a plus y. Yeah, okay. And what is phi? So this is quite a complicated little key change. Z a times c plus y plus 1 plus b plus d plus y acting on t. Okay, so what's going on? I will not derive the whole thing, but we can sort of trace at least some of what's going on. So the server, what's going on? The server first has encrypted this qubit and then sent it to Bob. And in addition, prepares a random qubit with, and they know exactly these parameters y and d. So it's one of those four states that I mentioned previously. Then sends this, that's what this line going up here means. It means it got sent to the client, sorry, the server, who performs T on the first one, does a controlled NOT, and then essentially teleports the state down to here onto the second qubit line. And essentially what's happening is the server then performs this PX, which will precisely undo the P that is obtained from the server applying the T gate here. So that's essentially, the idea is just basically that you want to teleport this thing and this correction, you want the phase correction that was showing up here to actually be corrected by the server, and this X is sent to the server from the client. So you require the ability to prepare this random state and also send one qubit of classical information to the server to do this. I don't know that it will be too useful for me to trace through how to pick up these signs, but the point is that up to you basically update the encryption key by A goes to A plus C, and B goes to this complicated okay. Yeah, so I think that you'll just have to trust me on this part. Is this okay?
I have a question, Simon. Is
Mhm.
the part starting from CNOT measurement and PX that? Oh, I see. The control is not coming from the measurement. It's an control because it looks like a T gadget, right? But it's not, right? Because
Well, it
control
kind of is though, right?
the control on this the P gate though, it's not the one coming from the measurement, but it's an arbitrary.
Well, I think that that's still in the T gadget. If you recall, the T gadget is something like it's something like this
Yeah.
T, and then there's like S X. Oh, well, I should use the same notation. I guess it's like PX or something. Uh, and this is supposed to be T psi. So let's see, what is the connection here? The control is going to, yeah, because, oh, I think it's very similar, right? Because this T gate, instead of having the T gate out front here, you've applied it to the plus state, for example, right?
Yeah.
So you can think of this as being like a plus and then T here. And then you measure,
Mhm.
which is exactly what's happening on this top line.
Mhm.
And then
Maybe that could help with the computation somehow, but otherwise, yeah, the control of the P's in your case is coming from somewhere else, right?
uh
Measurement is
yes, it
not related.
seems so.
But oh, A and Y. So what are they? So Y is on the
Y is
client.
coming from here, and then A is coming from the
Oh.
initial encryption here.
Mhm.
Yeah, so essentially it's all coming down to this commutation relationship, right? Um, so when you apply this thing and you try to start commuting it through, you are going to pick up an extra Z factor, the and an X factor here, um, and then this P. So this X equals A plus Y. Why is that? Because the Y is coming from this, and the A is coming from when you conjugate this through, I'll have a P to the A power here.
Yeah. Mhm.
Which is the thing that you're going to try and undo.
Mhm. Okay. Mhm.
Okay, so if you believe that this one is correct, so let's see if I'll have to maybe go just a few minutes over um, because I do want to say this is kind of an interesting part of the paper. So we have to take a detour to uh, so we have this that if you have a let's see. So if you have that H and K are, let's just say, I mean finite dimensional. And then you have that L of H, K are linear maps from H to K. These are maps M going from H to K that are linear. And then also sometimes we use L of H to imply that we just have a map M that's linear from H to H, also linear. Um, so this thing is a physical map if it's a quantum channel. And the reason that we have to introduce these channels is to sort of define the privacy. In principle, the client and the server could share some entanglement a priori between them. And so the client is going to maybe, or sorry, the server is going to try and use that a priori entanglement to sort of get some information about the computation that the client is doing. So that's sort of more naturally modeled using channels. So this is phys so let's say it's completely positive and trace.
I have a question. So your notation here, LHK,
Mhm.
upstairs stands for linear maps from H to K, and then do you mean in the second, I don't know which notation you follow, but is this a map? The phi, is it a, oh, it's a completely positive. So you mean it's taking
Uh,
L of H to L of K. So do you want to say like,
hold on, sorry. Yes, I think I miswrote something. No, this is a map from, yeah. Okay, I just have, it's completely just a mistake. Yeah, this is from L of H to L of K that is completely positive and I'll just trace preserving. So this is, it's a channel. And so if I'm given two channels, phi and psi, we can define the diamond norm. So this, you can think of this sort of more operationally as upper bounding the probability of distinguishing these channels in one shot. But I will just write down that there's a sort of definition of this quantity. Which is going to be precisely the max over all quantum states of the one norm of this quantity tensor identity on some auxiliary input space acting on rho minus tensor identity on W such that yeah, this is the one norm such that rho is an element of the quantum states potentially mixed on I guess it should be this. Okay, so this is the one norm. So this is going to come into the definition of how you define privacy and security. So let's okay, so suppose that we say that the computation, that is, you have this classical data, which is the sequence of gates that are to be performed. I will say that this sequence of gates in this classical data is, this is supposed to be L. Just some input classical data. So we define the sort of this privacy by first identifying, okay, so there's a client and a server in the case where they're honest, and there's the case where the server deviates and is malicious, and then we call this, when the server's deviating, you call it S prime because the client is always honest. So we let W be some output space for the deviating server. That we write as S prime. So throughout the course of this protocol, what you say is that the client server interaction induces a map. And what is that map? It is, depending on the computation itself, in principle it could, it is a map from L tensor V to LW, where this is the client quantum register, this is the server's quantum register, and this is the, what did I call this? This is just like the output space. So what is this trying to model? The idea is that in principle, the client and server, they have some joint quantum space that they share in which they're actually sending qubits and classical information back and forth. And this interaction induces a map in the sense that the client, or sorry, the server is going to try to extract some information maybe from this input state space and then perform some operations on it in some output space, maybe in order to get some information about the computation that's being performed. But just formally, this is what it means for these for the client and server to interact, and for the server to try and extract some information from this process. You have a map like this. I think that that's fairly general. So, and I already said this, that the server is trying to use this output space to obtain information about the client's computation. In addition to this, we also define a strange sort of notion from my point of view. You define another map which has the same input and output space. Let's see, actually. Also, this thing is called a simulator. Also, define a simulator, sigma q, which I'll explain in a second. You have this map, and such that row in gets mapped to this simulator acting on the partial trace. This is supposed to be U. So you trace out the client. So you define the simulator on each input Q in L. So what is the simulator trying to do? So the simulator is acting only on the reduced state with the partial trace that's seen by the potentially malicious server. So what the simulator is going to try and do is more or less, if I've understood this correctly, is that it is going to try and simulate the sort of interaction between the client and the server, acting only on this reduced state. And if the maps between these two things are sort of like, okay, so maybe it will actually be useful to say this first. So C and S are epsilon, or maybe just private. If phi q and psi q are indistinguishable, for every q in L, and in particular, you say that something's epsilon private if the diamond norm is bounded by epsilon. So you have q in L. So, okay, to go back to what the simulator is trying to do, the idea is that you want to basically show that for any interaction between the client and the server, there is a simulator which sees only this reduced state, and you can make this simulator as well approximate the actual interaction as you want. And in fact, the claim is that epsilon equals 0. So there's no amount of information that's gained by the server in this process at all. So I think that this part is a sort of, it's a really, really tricky proof that they do here. What they try and do is the following. So let me try and sketch it. It's pretty, so the idea is that you want to perform the encryption using teleportation. So I will sort of try to, and then use the principle of defer measurement to defer. So what do I mean by using encryption to perform encryption using teleportation? Essentially, you're using that teleportation circuit to, and then doing a measurement to put these random polys on the quantum state. And then you want to defer the measurement until the quantum register has been returned until the end of the protocol. In particular, the quantum register has been returned to Alice or to client. Which, and then at the end of this is when the client performs the measurement that was deferred. And then because they know the outcome, they know actually how to perform the decryption as well. Okay, so I'm sort of just sketching this, but why is this sort of important? So the idea is the following from what I gather. If you perform these encryptions, by which I mean you want to do something like this, right? If you instead implement this using a teleportation and then you defer the measurement all the way to the end, then um, then the server never actually there's no prior information about the actual encryption that the server can get any sort of information from because you don't even know what the encryption is. You're doing it using teleportation and then you're deferring the measurement to the end because there's no prior information about these A's and B's that the server can essentially get information from. Then I mean this is I think unfortunately, I think that the proof is written in this very like colloquial way, which I think I would have benefited from something a little bit more concrete, because maybe this is not so intuitive to somebody who's not a cryptographer. But my rough understanding is that if you perform the encryption, then use teleportation, but defer the measurement to the end, in the intermediate period before the measurements happen, there is no encryption key. Therefore, there will always exist a simulator who reproduces what the server sees, which is to say they will not actually be able to get any information from this because it hasn't happened yet. And then at the end of it, the client performs these measurements and can do the decryption. Um, I think that that's not well said on my part, but I didn't really understand this part too well, if truth be told. So maybe in a follow-up, we can discuss this more.
Okay. So I guess one question. So can I just ask something?
Yeah, sure.
Maybe okay. I guess I got a bit lost when you jump into channels, so I'm not exactly sure.
The channels are just really to formally define what they mean by privacy. I mean, this is you can think of it as just defining you have this client register and the server register, and
Yeah.
essentially you have the interaction given by a quantum channel that you would have if everything is just running according to the client and the server. And then you also have another map, which is a simulator. and the simulator only sees a partial reduced state. So the job of the simulator is to, from what I gather, I mean, you can just sort of formally define these things like this, and then you define privacy in terms of the diamond norm. So, I mean, that's just one formal way of doing it. And the reason that you need these quantum channels is because in principle, um, these operations, if Bob wants to, or I'm saying Bob, if the server wants to do anything malicious, the only thing that they'll have access to is a reduced state. So, in some sense, you have to use channels.
Okay, maybe I should ask in a way, what does this channel abstract or formalize in the previous scheme of communication, right? So we had this Alice and Bob, but then
Well,
the
so
tasks
the
be different
so
here.
the initial the domain of this thing is linear maps on U tensor V. So
Yeah,
U is the client's input space, and V is the server's input space. And so
yeah.
what this is formalizing is that, or maybe better yet, here, because this is the actual interaction. The idea is that row in could have some entanglement between the two. And Bob, the malicious server, is going to use some entanglement from this. In principle, there could be some entanglement that the client is trying to use to get information about Alice's computation, about her input state.
Hmm. Okay, but is okay. I couldn't still connect it back to the interaction of Alice and Bob in the previous. If you just go a little bit up here, for example, the T state case.
Mm-hmm.
So do we still have this sort of interaction here between Alice and Bob, or is this more general than, Alice having these kind of states, and maybe even in the previous case, it was even simpler type of
Yeah,
inter
but this is also a quantum channel, right? Of course,
So what is
which
okay, maybe I should ask directly, what is row in here, for example? How should we
row in, for example,
so that would be could be maybe the product state or
well, it
the
could be a product
on
state, but the thing is that that's precisely why you don't row in could be a product state, in which case I don't think that Bob will be able to get any information. But the point is that if they share a joint Hilbert space, it could be the case that there could be additional, okay, so how would I say this? Uh, So this is on the server's end. This is actually all, no, it's a little bit tricky, I think. Your question is what the initial input state is. So
yeah,
initially, I think that the input state's completely general, right? So what Alice sees, what the client sees is a product state. She's preparing a product state for her qubits. But that entire state, system A could be entangled with system B, which is the server, right? Like I could have something like this. Um, I could have, maybe I shouldn't use the same system A. This thing is a product state in itself, but it's tensored with some, mhm. Okay, psi B plus, okay. Hmm, 1 second. Okay, but yeah, I see what you're saying.
I'm not sure if I'm correct, but maybe I'll just add something in case it's helpful.
Mhm.
So I was thinking of row in kind of as representing a possible attack from Bob. Um,
Okay.
like row in being some state, we don't know what, but Bob wants to do some computation on it to learn more about um, what Alice is up to.
Yeah, that's my understanding is that like a priori, it's not just the case that Alice is preparing her qubits and then sending them to Bob. It could be the case that Bob is trying to, I mean, by giving a joint register, what you're trying to say is there's a possibility for yeah, what you're calling a malicious attack is essentially like he's got some entanglement with Alice's state, right? In which case he's gonna, because if it's just completely a product state and it's completely producted away from Bob's, can he learn anything about that? Well, I don't think so because you already have the one-time pad on it.
Yeah, yeah, I agree. Yeah, I think
So I think that the only way for Bob to be able to get any sort of information from this so that his reduced density matrix is not just a completely mixed state is that he's got some additional entanglement with Alice's. That's how I sort of understood it.
yeah, 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 I agree.
I
I
mean, I'm
agree.
not going to die on that hill because I found this part to be a little bit um I think if you're not coming from cryptography, some of the arguments are not that intuitive. Like, I don't exactly know what you have to look into these like like these interactive proofs maybe and this other sort of um, topics, which I'm not like well versed in, I think.
Yeah, yeah. So, but I think you're right that if you disallow entanglement, the proof of security becomes much easier, like almost trivial.
Yeah,
Uh,
that was what I was going based off of. Like, if you just don't allow any entanglement, then everything's kind of trivial. So the only way that things become interesting is if you have some initial row that could be entangled or any arbitrary state, and you model this gaining of information by this quantum channel, which maps that initial quantum state to some output on L of W, which is representing Bob's intention to sort of manipulate his, whatever reduced density matrix he has.
mhm. Yeah, and then the simulator is just showing that whatever Bob can do computationally with the help of the interaction, he could also just do on his own with his own
Yeah, exactly.
side of things. Yeah, yeah. So I agree there. I think that's all I had to say. Yeah.
Okay, yeah. I happy to discuss this more, Daniel. I think there are some subtle, it's a really actually interesting proof. Like I mean the proof is quite ingenious for this epsilon equals 0. You introduce some teleportation, you use deferred measurement and say because the measurement hasn't happened, you're able to basically say that this simulator must be able to be indistinguishable uh from the actual interaction. I think it's pretty nuanced, and I don't think I fully appreciated it, if I'm being honest.